Hello dear students, welcome you all. So in this lecture, I am going to discuss about the QPSK demodulation, right? You can see here, QPSK means Quadrature Phase Shift Keying, right? So in the earlier lecture, I have discussed about the QPSK modulation, right? And now in this lecture, I am going to discuss in details how QPSK signals are demodulated or extracted, right? So we know very well that QPSK is basically a kind of a M array, right? Modulation technique with M is equal to 4, right? And it can be further divided into two streams, conventional QPSK and pi by 4 QPSK, depending upon the value of a constant. If the constant is equal to pi by 4, then this is called pi by 4. I missed 4 here. So it is called pi by 4 QPSK, and if constant is equal to 0, then it is called conventional quadrature phase shift keying, right? So all these things has been discussed in the previous lecture. We know very well that how QPSK signals are generated. What is the procedure? So we have seen that in that case, first of all, the incoming bit stream is separated in terms of even bit stream and odd bit stream, and we represent that bit stream as a odd bit stream and B even bit stream. We also know that the odd bit stream is in phase signal or in phase bit stream, and even bit stream is a quadrature or out of phase we can say bit stream, right? So the first and foremost thing in QPSK is to separate the incoming bit stream into two parts, and then after we have taken two carrier waves having same frequency but the phase difference is of pi by 2. I mean they are 90 degree out of phase, right? One we can say one is cos of omega ct, so the other will be sine of omega ct. So these two carrier waves are used to modulate these two different bit streams, and then after these two modulated carrier waves are joined together with a adder, and according to that we get the output quadrature phase shift keying modulated signal. So this was the entire process that I recalled here. We also know very well that in particularly in case of pi by 4 QPSK, because I have discussed it in detail in that lecture, because it is usually asked in examination, and it is the important in the two QPSK techniques, conventional and pi by 4. So we have seen that in pi by 4 QPSK we have different symbols. Symbols means the phase levels, right? In the modulated carrier S1, S2, we have represented them as like that, right? And we know very well that S1 corresponds to bit stream when B odd bit is 1 and even bit is 0, then 0 0, then 0 1, and then 1 1. So this was the entire things that we have discussion there. So I am showing you the table that you can recall that here. This is the pi by 4 QPSK symbols and their corresponding phase shift. So I have recalled this table here. You can see here, right? This is input bit stream that has been separated into in phase and a quadrature phase bit streams, that is 1 0 0 0 1 0 1 and then 1 1. The corresponding symbols are S1, that is equal to a cos of omega ct plus pi by 4, S2 is equal to a cos of omega ct plus 3 by pi by 4, then 5 pi by 4, and then 7 pi by 4. These are the corresponding phase shifts, right, in the resultant modulated B QPSK signal, right? So all these things and this table has been explained in that lecture, right? Now I am coming to the detection or demodulation part of this B QPSK signal, right? We know very well that B QPSK signal can be represented as, if I represent it in a very simple way, then V odd t into, cos of vega c t. If I took the amplitude 1, then plus B even t sine of vega c t. So this is the output of the BQPSK. Right? Here I have taken amplitude is equal to 1. So this is the resultant, right? BQPSK signal that is received at the antenna. Now, how this signal is decoded? You can see this signal. If I ignore the these two terms, then this signal contains the information in two sides. One is odd bit stream and other is a even bit stream. So somehow we have to recover these bit stream from this BQPSK modulated wave, right? So for the detection of QPSK, we can use synchronous as well as non-synchronous or non-coherent detection method. But here the method that I have discussed or covered, it is synchronous, or we can say coherent detection method. We know very well what is the synchronous or coherent detection method. In synchronous or coherent detection method, the first and foremost thing is to recover the carrier wave, right, from the incoming modulated signal, right? So the same process has been done here. This part of this circuit or this schematic diagram, I will not call it circuit, it is a schematic diagram. So this part up to this, right, it is the recovery of the carrier wave, right? You can see. So the received here we have received that signal at the antenna, then that signal is sent to here first of all. So the first and foremost thing is that signal is multiplied with multiplier and it is raised to the fourth power. Or I can say simply, if I take the cos term, then suppose it becomes cos power 4 vega c t. Again I have taken the amplitude as 1 for simplification, right? Then after, what we will do, we will pass it through the band pass filter. So what band pass filter will do? It will convert into cos of 4, right, vega c t. It will convert it into this band pass filter, right, cos of 4 vega c t. I mean, it will expand it. Cos power 4 vega c t. It can be expanded by using the formula of a trigonometric formula of cos, right? Then after, we are using frequency divider network. What is the role of frequency divider? It will change this cos of 4 vega c t into cos of vega c t, that you can see here, right? So this is the process of extracting the cos term. We are only extracting cos term. In actual, it contains both cos as well as sine, but we have only here in this starting section, we have only multiplied with the cos term. So other terms are ignored. We take into the consideration only cos term, right? So we got cos of vega c t, or I can say 2 pi f c t here. Then this signal is passed through a 90-degree phase shift circuit. So I got sine of 2 pi f c t, or I can say sine of vega c t here, and it is cos of vega c t here. So cos of vega c t is applied here and sine of vega c t is applied here. Now these two circuits, this one and this one, you can see here, they are doing the purpose of a product modulator. Again we are doing the multiplication product modulator. The one input of the product modulator is the incoming signal, right, directly coming from the antenna, right, here and here, and the other input is the recovered carrier wave, right? For one modulator, product modulator, we are using cos of vega c t, and for other we are using sine of vega c t. So what will be the output of that? Again, I am taking the consideration for this. I am taking the consideration of cos of vega c t. So what will be the result? The result will be obviously I will get after the modulation, this cos of vega c t term will get squared, right? But I will have a v of t, right? I can say the input bit stream into multiplication amplitude of this already taken 1 into cos square vega c t. Similarly here, I will get in this particular case b of even t, right, into sine square vega c t, right, because here we are multiplying it with the sine. So you can see here b QPSK sine of, they have considered only sine of vega c t here, and here they have considered only cos of vega c t. The other term is ignored. We can use do it in the circuit actually. We can extract the other term. We can only consider the cos term, right? So then after this product is passed through a integrator, and the integration is taking place within the limits, right? The limits are the according to the bit rate, right, and they are for the 2-bit interval, right? That's why we have taken it 2. So then after doing the integration here, I am able to get b output of t multiplied by some constants. I can ignore them. B output of sorry, not b output, b odd t, that I was talking about, and here I will get b even of t. You can see here. Now these two odd bit stream and even bit stream, basically they are not bits at this point, but they are contained in this entire signal. It is multiplied with some other constant terms. So obviously it is a variation that can be positive or negative. We know very well that odd bit, this odd bit can be positive, can be negative. Similarly, this bit can be positive, can be negative, because we have used the NRZ, a bipolar NRZ that converts 1 into +1 and 0 into -1 volt. So according to that, whatever bit stream is coming here, we will get some voltage, and then that voltage is applied to a decision making device whose threshold value is taken as 0. It means if the incoming voltage is positive, it will generate 1 bit, right? But if it is negative, then it will generate 0. Similarly, the same logic is here. If the input bit stream, or not bit stream, but if input coming voltage is positive, then bit is +1, and if it is negative, it is 0. Again, here we are taking the threshold level of this decision device as 0. So we are now getting 2-bit streams. One is a odd bit stream and other is a even bit stream. So once again, the next task is to join these 2 bit streams together. So we are using here parallel to series converter, right? In the beginning, in modulation, we have used series to parallel converter, right? But here we are using the reverse, parallel to series. I mean, whatever parallel data, these 2 bit streams are parallel, right? So we are converting them into a series form, right? I mean, if I am getting 1 1 0 here and I am getting 0 1 0 here, then I will get 1 1 0 0 1 0. Now it is the series format, kind of that you can say. So in that way, we are capable of recovering the original bit stream that was used in the beginning when the modulation took place, right? So this is the working of this entire QPSK demodulator, and it is a synchronous or coherent modulator, demodulator, right? The process is first of all extraction of the carrier wave, and then taking a phase shift, because it has been done in the modulation also. Then after taking again to product modulator, then integrators within proper limits, and then extraction of the bit stream. So I can show you a table here that can show the received QPSK signal and demodulated output bit stream. So you can see if this output bit stream, right, this is positive, B odd is positive, then it is 1, and if even is negative, then it is 0. Similarly, if both are negative, then the bit stream is 0 0. If this is negative, this is positive, then it is 0 and it is 1. It is positive positive 1 1, right? These are the different symbols, and you can see here also it is positive, and the second term is negative. In this, both the terms are negative. In this, only first term is negative, both are positive. So this is the same table that I have discussed in case of the modulation. So in this way, we can recover the in phase and quadrature phase bits, and then after these two bits are joined together with the help of a parallel to series converter. So this is the way of recovering the QPSK signal. Now I am coming to the some advantages and disadvantages of QPSK. First of all, I am coming to the advantages. So the major advantage of QPSK, I told you in that lecture also, it is the reduction in the required bandwidth. It is nearly half of the B.Sc modulation technique, right? So obviously when the bandwidth is reduced, requirement of the bandwidth is reduced, the bit rate is increased, the efficiency is increased. So this is the major advantage of this QPSK technique, right? If I come to the disadvantage, right, the disadvantage is that it is difficult to design the circuits for the extraction of and generation of the QPSK signals, right? Also, as there is a change in the phase, right, we are using 4 phase angles, so there is always a probability of the introduction of the errors or noise in the modulated and demodulated signals. So that things has to be taken into the consideration, right? As far as applications of this QPSKs are concerned, then applications these QPSK modulation technique and demodulation technique is oftenly used in mobile communication, that is GSM, or it is CDMA, right? Code division, multiple access, global system for mobiles. It is also used in LTE, that is nowadays commonly used, long-term evolution. It is also used in satellites communication, as well as cable TV, right? So all these are applications where QPSK can be used, right? This is all about the demodulation of QPSK signals and advantages, disadvantages, and some applications of QPSK modulation technique, right? So thank you very much.